Good afternoon. So today we are going to be talking about linear and projectile motion. So in your science textbook, this beautiful guy, you're going to open up to page 10, and page 10 is the start of chapter 2, linear motion. So we're going to do a little page walk. I'm going to talk through the important stuff. You're going to jot down some notes, and then we'll be in great shape. So let's start at the very beginning with the idea that motion is relative. So what motion is relative means is motion is based off of your own perspective. For example, if I asked you, how fast are you moving right now? Well, the easiest answer would be to say 0. I am not moving. I am sitting still in my chair. However, you could also say, well, you're on the Earth and the Earth is spinning. So maybe you're moving at 1,000 miles an hour because the Earth's spinning rate has you going at 1,000 miles an hour. Or that would be from the perspective of somebody standing on, say, like the North Pole, right? Just out in the atmosphere, orbiting around the Earth at the North Pole, you'd be moving at 1,000 miles an hour. Or you could say, well, the Earth is also orbiting around the sun, and that has you going at a few thousand miles an hour. Or if I'm at, say, the center of the universe, and I say the universe is expanding and you are part of the Milky Way galaxy, well, then you're moving away from me at millions of miles an hour. So the motion is relative. Another way of thinking about this is if you are on a train or in a car or on a plane and there's somebody sitting next to you, from your perspective or from my perspective, if I turn and check, this ball is the person sitting next to me, obviously. So I turn and check, that person is not moving. Check back, still in the same place, still not moving. However, from the ground's perspective, if I'm on a plane, I'm moving at 500 or 600 miles an hour, right? I'm flying along, or if I'm in a car, I'm moving at 60 miles an hour. So this person could be moving not at all, or they could be moving at 600 or 60 miles an hour, depending on your perspective. So motion is relative. Okay, speed. Speed is how fast you're going, distance divided by time. We should be good with that one. It's in your physics everything sheet already. Flipping on to page 12. On page 12, there is a nice little diagram, and I'm going to pull up that diagram for you now by sharing my screen. There we go. And seeing how that goes. All right. So if I pull up the top of page 12 is table 2.1. And on table 2.1, there it is, it looks like this. So it just has a nice comparison point from kilometers per hour to miles per hour to meters per second. There are approximately 2.2 miles per hour in 1 meter per second. Now, that's not precise, but it's a good enough estimate where you can double it, add a little nudge, and you're pretty much there. So for example, if I got 6 meters per second, double it, 12 miles an hour. I didn't add the nudge there. 11 meters per second, double it would be 22. Add a nudge, puts me at 25 miles an hour. Let's say 22 meters per second, double it, 44, add a nudge, and I'm at 50. Okay, so pretty much double it plus a bit. I say it's about 2.2 miles an hour in a meter per second. So that gives you a rough approximation of about where you'll be. Okay. Now, the difference between instantaneous and average speed. Instantaneous is how fast it's going right at that instant. So for example, in your Rube Goldberg machine, it was the difference between average velocity and final velocity. Final velocity is twice as fast as the average. That makes a big difference. So we mostly want to pay attention to the instantaneous speed or the instantaneous velocity. That's the one that will be more important. All right, velocity includes both direction and magnitude. So it's speed in a certain direction. So what that means is if I'm going the same speed, let's say I'm standing back here and I'm walking in a circle, right? And I'm going to go the same speed. I'm always going to go 2 miles an hour. But pay attention to my direction. I'm holding my arm out straight in front of me, and my direction is constantly changing. Sometimes I'm pointing at the front of the room, sometimes I'm pointing at the back of the room, sometimes I'm pointing at the side of the room, and it's changing constantly. So I have a constant speed, that stayed the same, 2 miles an hour, but my velocity was always changing because my direction was always changing. Acceleration, already in your physics everything sheet, change of velocity over the change of time. Lovely. Free fall, how fall and how fast. So if I drop an object from a height like this, whoop, it will accelerate at the constant acceleration due to gravity. We know that that's 9.8 meters per second squared. Your textbook uses 10, they round it, that's fine. What that does for us is it tells us if I know how long something has been falling, I can figure out how fast it's falling, because acceleration is the change of velocity, meters per second, every second per second. So meters per second squared. So every second, I will gain another 10 meters per second of speed. So after 1 second, I'm going 10 meters per second. After 2 seconds, I'm going 20 meters per second. After 3 seconds, I'm going 30 meters per second, et cetera, et cetera, et cetera. So I take the time, multiply it by 10. I'm going that fast at that point. All right. So that's great. Flipping on now to page 18. I'm now on page 18, and I see this nice diagram of a person throwing a ball up in the air. Looks kind of like this, standing on a cliff. So here's the big idea. When throwing an object in the air, assuming no air resistance, the path up is going to equal the path down. If we pay attention here, this path up right here is equal to this path down right there, right? Up equals down. It also means that the time up is equal to the time down, because the only force acting on it is the force of gravity. So it's up, 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 stop, down, 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 down for an equal amount of time. I also know that the velocity up is equal to the velocity down, because the distance up is the same, the time up is the same. So if the distance and the time are the same, the velocity has to be the same. So the velocity up equals the velocity down. The acceleration all the time when it's going up and when it's going down is still down. The acceleration is always down because gravity is pulling it down at 9.8 meters per second squared. Now, this feels a little bit counterintuitive because we would think, well, no, it's moving up at the beginning. The velocity is up, but it's slowing down. And since the velocity is going from big up to small up, the change of velocity is in the downwards direction, right? So I'm going from big up to smaller up. If I compare this versus this, my change is negative, it's down. And that would be my acceleration, right? This would be my velocity at the first section. This would be my velocity at the second section. And if I did velocity 2 minus velocity 1, I would see that the acceleration, the change in those velocities is downwards. It's negative. So it's 9.8 meters per second squared down. Okay. Also, I know that at the very top, right up at that top section there, the ball is going to stop for a fraction of a second because it's going from up, up, up to down. So if I demonstrate that, I have a ball here. I throw the ball up. It's going to go up, 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 stop, down, 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 down. All right, let's see if I can do that. Up, stop, down. Stop, down. Right? Up, stop, down. Okay. Acceleration continues to be downwards, velocity going up, less, 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 0, velocity going down, small, big, 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 big. All right. Free fall, how far and how far? Well, we can figure out how far an object is going to fall using the equation distance equals 1/2 at squared. So I have this equation, d equals 1/2 at squared. t would be the time, a would be my acceleration, and d would be the distance that I'm traveling. So for a falling object, I could do 1/2 the acceleration due to gravity times the time that it's falling squared. Now, I'm going to take, if it's going up and down, I would just take half the time, because half the time's up, half the time's down. If it's just a pure drop, I would take the whole time because it's falling the entire time. All right, so that's d equals 1/2 at squared. Flipping on to page 23. Page 23 shows me some graphs of motion. So I'm going to add those in. I have velocity versus time. So here would be a time, velocity, meters per second, and time is in seconds. And what I would see is for an object free falling, so these are all for free fall, the velocity versus time graph is going to be a straight line. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 10, 20, 30, 40, 50. So they end up matching up with each other perfectly. At 50, I had, at time 5, I have 50 meters per second because the acceleration was 10 meters per second per second. Okay. So that's velocity versus time. And then distance versus time would look a little bit different. I'd still have my time in seconds, and this one is my distance in meters, and my overall shape would be exponentially curved. It's not actually exponentially curved, it's quadratically curved, it's a squared. My mistake there. So 5, 4, 3, 2, 1, and this would go up to a maximum up here of 125 meters. And then at time 1, it would be 5 meters. At time 2, it's 20, sorry. So this is 1, 2, 3, 4, 5, and this would be 5, 20, 45 at 3, 80 at 4, and then 125 at 5. Okay. So there's some graphs there. All right, so that's chapter 2. Let's go straight over to chapter 3. So chapter 3 starts on page 28, has this nice picture of a cat jumping in a parabolic projectile fashion. Good job, cat. All right, so let's take a look at chapter 3, and chapter 3 introduces the idea of vectors. So a vector and a scalar quantity, we've mentioned, a vector has direction, a scalar just has the magnitude, so it's just a number. So let's talk about adding vectors. I can add vectors by putting them tail to tip. So let's say I have two speeds, 100 kilometers per hour and 20 kilometers per hour. Well, if I have my 100 kilometer per hour speed here, I'm going to represent it with a line that is representationally the same size as 100. So I chose 5 centimeters, right? 5 centimeters is to 100 as 1 centimeter is to 20, right? Because 20 is 1/5 of 100. So this would be like 5 to 1. And then I've put them tail to tip. So tail to tip vector addition means I take the tip of my first vector and put the tail of my second vector up against it. Then when I add them together, I can say, okay, 100 plus 20 gives me a grand total of 120 kilometers per hour. So if I have a plane that's traveling at 100 kilometers per hour, and then it has a tailwind blowing behind it, pushing it along at 20 kilometers per hour, the plane's total speed with respect to the ground would be 120 kilometers per hour. What if the wind's blowing the other way? What if instead of blowing my plane forwards from behind, the wind is blowing into its face, the wind is blowing against it, and pushing it backwards? Well, I'm still going to do the same thing. I'm going to do my tail to tip addition out here. And in this case, I start with my blue 100 km/h vector. There she is. Then I'm going to say, here's my tip of my previous one. That's going to be where I start my tail of my next one. I drew it a little bit lower so I could see it. And there is my second vector, my wind pushing back. And what that leaves me is that to that. So beginning here to, sorry, the beginning is over here to the end over here. And I can draw in my resultant vector. My resultant is what I'm left with, right? And I see that my resultant is a grand total of 80 km/h in order to get to the end of the arrow. Okay? So the red ones are called resultant vectors. It's basically like the sum of two vectors. It's the sum of two arrows. All right, now we can also do that in 2 dimensions. So far I've been assuming everything's traveling on a straight line. That's just 1 dimension, but the world is a little bit more complex. You know, the world actually has 3, or if you count time, 4 dimensions, or more than that if you want to get really crazy. But let's start with 2. We've gone from 1 dimension up to 2 dimensions, which means now instead of going straight line, I could go straight line on a plane, right? So sideways and front, forwards, and backwards. Whoa! Okay, so let's take a look at the next example. So if I flip over to page 30 and 31, okay, page 30 and 31, I would see if I have a starting point of 2 vectors. I have an 80 km/h vector going to the right, and then I have a 60 km/h vector going up and down. Maybe now the wind has shifted so that it's blowing to the side at 60 km/h. What I'm left with is 80 and 60 at a right angle to each other. So one of the ways that I can solve that is by drawing my resultant vector, right? I can draw my red arrow going from tail all the way out to the tip, right? There's my tail to tip vector addition. And again, I went out to here. There's my tip that leads to my next tail, boom. Now I have a triangle, and in order to find the lengths of a triangle, I could do a squared plus b squared equals c squared. That might look familiar to you as the Pythagorean theorem. And I could put in 60 squared plus 80 squared equals c squared, and c ends up being 100 km/h. Or you might recognize this one as 60, 80, 100. That's like 6, 8, 10, which is the same ratio as 3, 4, 5. And you might remember, hey, that looks a lot like this 3, 4, 5 right triangle. So if you notice that the sides are equivalent to a 3 and a 4, or they're in that ratio, then you know that the hypotenuse is going to be a ratio of a 5. So 60, 80, 100 is a 3, 4, 5 right triangle. Another example of a 3, 4, 5 right triangle, or sorry, not a 3, 4, 5 right triangle, but another common right triangle that you might see is a 45-degree angle. So a 45-degree angle, because this angle is equivalent to this angle, I know that the 2 opposite sides have to be equal to each other. So I could say like that side has to equal that side. And so I'd say this side is 1, right? Let's give it a measurement of 1, and this side is 1. And then 1 squared plus 1 squared, take the square root, is the square root of 2. And a square root of 2 is about 1.41. So another option is if it's a 45-degree triangle, it's going to be 1, 1, and 1.41, or the square root of 2. All right. So we've already seen this as like a perfect triangle, but I could also draw it in another way. I could also draw it not as a triangle, but as what I'm going to call a deconstructed triangle. where I've taken my y coordinate, or my up and down arrow here, right, that guy there, and I've just moved it over to the other side so that it sits there, right? If I just shift it over, it's the same vector, but in a different location. And then it ends up looking like this. And I can say that this part is the horizontal part, this part is the vertical part. I could also call this the x component and this the y component. Either way is fine, but it leaves me with my resultant vector in red right there, going all the way to where they connect. All right, so velocity can have both horizontal and vertical components. Now, when we look at velocity, and we know that there are horizontal and vertical components of it, one thing to keep in mind is that horizontal motion is totally independent of vertical motion. Horizontal motion remains constant, right? Horizontal velocity should always stay the same unless there's a force of friction against it. Vertical velocity will always be changing because the vertical velocity has acceleration down at 9.8 meters per second squared, right? So we're always going to see the acceleration downwards. So if I compare these two balls, the red ball is falling with no horizontal motion, right? It has 0 horizontal motion. And so the red ball goes from here to here to here to here to here to here, et cetera, right? It's just dropping all the way down. Boom, 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 boom. But there's no horizontal part. It's not moving side to side at all. The yellow one has a horizontal velocity. It was pushed sideways as it started to fall. They were both released at the same time, and then they took pictures every fraction of a second. So the yellow one, its vertical part is exactly the same as the red one's vertical component, right? They match up 1 to 1, but it has the additional horizontal component to it. So horizontally, it's moving sideways a little bit, right? Every fraction of a second, it moves another fraction over sideways, right? So every little fraction, it's moving over the same amount sideways, which is equal to its horizontal velocity. So I can treat horizontal and vertical motion independently of each other. I don't have to consider one to pay attention to the other one. All right, so that is helpful. Then I can also say, actually, this is kind of fun. So I could draw out a motion diagram. If you check page 36, you could see how the horizontal and the vertical components change at different parts of the parabola. If I pay attention to the shape of an object going through the air, it's a parabola, which you're going to study parabolas in algebra if you haven't already. And this is where parabolas become interesting, is that parabolic motion is the shape of any object flying through the air without friction, without air resistance. Okay, so theoretically, if I kicked a ball or threw a ball, I could pay attention to the angle that the ball leaves at. The angle is called theta. And I could pay attention to that angle, and that would tell me about how far the ball can go. So if I kick the ball at a really gentle angle, like a 15-degree angle, the ball doesn't go very far horizontally because it's not off the ground for long enough, right? It goes up, it's going fast sideways, the horizontal part is big, but the vertical part's not big enough to keep it in the air for long enough. If I go 30 degrees, now I'm able to go a little bit further. But if I want to go the furthest, I want to go with 45 degrees because a 45-degree angle will keep me in the air for just long enough to take the ball the furthest distance. If I go to 60 degrees, the ball will be in the air for a really long time, but its horizontal component's not big enough, so it doesn't go as far. And then 75 degrees, same deal. It's going really high, but not far enough. What if I want the ball to just go as high as possible? If I want it to go as high as possible, then I should just go at 90 degrees, right? Because 90 degrees would go straight up and then straight back down, right? It would not go horizontally at all, but it would go the highest because that would be a 90-degree angle straight up. All my motion is vertical and then straight back down. Okay, so 45 degrees is the ideal angle for maximum distance, assuming no air resistance. In the real world, air exists. That's good for us breathing. It means that the balls aren't going to go as far as we would calculate them to at a 45-degree angle. So if you want to maximize how far you throw a ball or kick a ball, you are actually going to aim for more like a 25 to 30-degree angle. If you look at most major league home runs, they're in the 25 to 30-degree launch angle. That's to maximize how far the ball goes so that it goes all the way out and over the fence to count as a home run. If you hit at a 45-degree angle, it's going to be more like a pop-up, right? It's going to go up and then come right back down into the outfielder's glove. Or if you hit it like 60 degrees, now you're in like the infield pop-up, straight up, straight down, and the second baseman just catches it right there. So you're aiming for 25 to 30 degrees for hitting home runs. All right, and that puts us in great shape. So now we're going to do the Chapter 3 practice problems. Have fun with those, and I will post the key very shortly. Enjoy.